So the basic idea behind average is linking UQ and models and making that easier in practice. UQ problems that we might look at is, for example, uncertainty propagation, where uncertain initial data lead to uncertain predictions, in this case indicated by this white cone. And it's quite important in applications like this that we actually know the degree of certainty because, well, given our current best knowledge, the best fit prediction essentially is this skinny black line. But as the US Hurricane Center tells us, we're essentially not supposed to look at that. We're supposed to look at this wide cone of possible paths that follow from our uncertain knowledge about the current state. And of course, in this application, that's really important. And the same goes for something like nuclear waste storage. If you want to be sure that given your subsurface composition, a nuclear waste storage is still going to be safe hundreds or thousands of years to come, even if there's a leak. So there's a wide variety of methods how we can solve problems like this. And I think this is really justified because there's fundamental properties in which these methods differ. So some methods, for example, need to have very detailed knowledge about your simulation models. Others might make only very superficial assumptions. They differ a lot in what they tell you about the um, statistical distributions that we are looking for. So you might only get an expected value. Other methods might give you an entire probability distribution of outcomes. And of course, methods differ a lot in efficiency. Now, these goals, being as model agnostic as possible, being as expressive as possible, and being as efficient as possible, are mutually exclusive to some degree. So all of these methods find themselves somewhere in that triangle. And importantly, I'd like to bring up that we still may have to go to high-performance computing resources in order to scale up applications like this, because even the most efficient methods, if you throw them at really compute-intensive simulation models, may still need quite a lot of compute power. So how can we solve this? One example for inference under uncertainty is Markov chain Monte Carlo. The idea is that in this simple example, we have two model parameters that are unknown, and we have observed data that come with some uncertainty. So think of measurement errors, for example. We would now like to know what parameters are likely given the data that we have. Following the idea of the Bayesian framework, and I'm not going to show the math here, we simply say that a parameter is likely if its corresponding simulation output corresponds to what we've observed. So essentially, we'll take a parameter, plug that into our simulation, and if the outcome matches what we've seen in the real world, we'll say it's likely. If we plug in a parameter and the simulation output is very different, then we're going to say this is not likely. In the end, this kind of formulation allows us to retrieve an entire distribution of parameter values that are likely given the observation that we have. Now, a deterministic inverse problem might just give you the most likely point in the distribution, so essentially the best fit of parameters for your simulation to recover what we've seen in the real world. But it's really quite important in many applications to know that distribution, since in examples like nuclear waste storage, for example, you would of course want to be sure that all parameters that are plausible given your data are actually on the safe side. And you want to really exclude that there's something like a little part that has maybe 5% probability that would actually be critical. And that's somewhat far away from your data, but not impossible given your measurement errors, right? So there's really quite a value in understanding these inference problems. Now, I've already kind of shown how you can determine for one point whether it's likely or not. And that is, again, run your simulation, compare to data. If it's close to what we've seen, this parameter is likely. This tells us if a parameter is likely. It does not yet tell us what parameters are likely. So we need a method that actually recovers this distribution. Markov chain Monte Carlo does this by starting with a random starting point and picking a random point in its vicinity. We're now going to run the simulation for both parameters. And in this case, we'll find out that the proposed parameter leads to a simulation output that is much less close to the observed data than our starting point. So we'll say this is very much not likely, and Markov chain Monte Carlo is most probably not going to step there. We'll try this a couple of times until we find a proposal which actually leads to a simulation that comes closer to what we've seen, and in which case we're guaranteed to move there. Now, even if the probability is a bit lower, there's a chance we might move there. And the result is essentially a random walk across our parameter space, which, well, for many, many samples, is going to converge slowly to the distribution that we are looking for. Each time running the simulation, each time comparing to data. And in the end, we can take these samples as a representation of the distribution and say that 95% of our samples, in other words, 95% of our probability distribution, is, for example, on the safe side. And then it's a matter to decide in practice, can you live with, let's say, 5% risk of something bad happening? Of course, that entirely depends on your application. And the outcome might be, well, we need more data, or we need to change something about our physical setup and increase safety margins and so on. So I hope this gave you a rough idea of how you might, in a very basic sense, solve these UQ problems. Now, what we've just seen is that we actually need quite a lot of simulation runs with these basic methods. So we need some way to gain more efficiency. And this is just a bit of an outlook, just to throw the idea out there. We're not going into details. We've seen multi-level methods yesterday already. The idea is that if you're given a UQ problem that has a very compute-intensive simulation model, something like Markov chain Monte Carlo in its basic form, like we've just seen, is not going to work, because we have to run this entire simulation of a tsunami wave originating from some point that we're looking for, and compare to data for each and every point of this MCMC procedure. The idea behind this is, well, or let's say the problem formulation is, of course, we have the observed data from buoys. We want to find the source of the tsunami. Again, running all these simulation runs with MCMC is not going to do the trick. So we are going to get ourselves, and that's specific to multi-level methods, an entire hierarchy of approximate simulation models. So rather than just operating on the fully resolved one, we got ourselves models that have a coarser mesh resolution, and that might actually be simplified in some other ways. For example, here we are smoothing out the bathymetry, in other words, the ocean floor, which means we lose some of these small islands that you see on the right-hand side. And that just happens to be advantageous for the particular kind of simulation method or the particular PDE solver we have in this case. And on the left-hand side, we have what I call a tsunami in a bathtub, so just linear seafloor, which is, of course, going to give us a very wrong result, but maybe still good enough to give us a better starting point than just performing MCMC on the finest. Now, the idea is that in the end, we really just perform Markov chain Monte Carlo on the tsunami in a bathtub, and we're going to use its outcomes as proposals on the next final levels. So in contrast to this MCMC that I've just showed you, where we're just blindly walking through parameter space, in this case, each proposed step will already come from the next coarser level. And assuming that these models approximate each other well, you can kind of see here now that this distribution is quite wide, but it still encompasses well the distribution that we are looking for at the intermediate level. The same goes for the finest. So the result is that we actually need very few samples on the finest level, very few simulation runs, at the cost of doing a lot of runs, but with very fast models. So I hope this kind of gets across the idea that we can actually do really interesting things on the UQ side in order to increase efficiency, specifically when it comes to reducing the number of simulation runs that we need for an accurate result, even in really high compute-intensive simulation problems. By the way, this application we still had to run on a couple of thousand processor cores. So that's great, isn't it? We can now do UQ in general. We can even do it for very compute-intensive models using advanced UQ methods. So why is it not happening by default, right? After all, it would be really helpful if every simulation result and every inference problem that we solved gave us this measure of uncertainty and this confidence in that our results are fine, or at least an indication that there is a problem. So despite its use, why is it not just coming by default? And I think one of the main reasons is overall complexity. We now have to combine methods from uncertainty quantification, which are more on the statistical side, basically, with the numerical simulation of forward models, which themselves could be very complex and have to be efficient. And even then, we may have to go to high-performance computing systems, And now you're combining expertise and tools from 3 different fields in order to solve one scientific application. And I think this really leads to sort of a divide in the community where we have a lot of UQ method research happening, but that is often only applied to relatively simple model problems. On the other hand, we have really advanced models and simulations from applications across science and engineering, but those often have to resort to simple UQ methods like plain Monte Carlo or plain Markov chain Monte Carlo, like we've just seen. Now, in my opinion, the truly interesting thing happens up here when we're combining really interesting simulation models that are really compute intensive with advanced UQ methods, because now we can actually perform proper UQ at high accuracy in truly interesting simulation problems and answer truly challenging real-world questions that are much less intuitive than we would have in the case of much simpler models. Right? Now, I'm not saying that this up here is not happening. There are applications that really bring together the best from both worlds, but they are often sort of one-shot solutions that can't easily be transferred to other applications, and they require massive engineering effort. So often we see that by the end of setting up a UQ problem in this corner, people have a PhD. We'd like to change this, right? We'd like to move up here in this top right quadrant. So Umbridge sets out to facilitate this on a technical level by allowing us to split UQ applications into a distinct UQ and model side. The idea is that rather than building one single application that covers all 3 aspects, we have a standalone piece of software that handles the simulation model. We have a standalone piece of software that handles UQ. Now that gives us a lot of flexibility. Part of it is, of course, we can now take the typically written in higher level language UQ packages and combine them with low level simulation codes. So we might have a UQ code written in MATLAB, which is perfectly fine because UQ itself is typically not too compute intensive. It's the model setter. We can link that to Fortran written codes, possibly running on clusters. And Umbridge also really handles scaling up on clusters as well, which allows us to separate concerns now between UQ experts, simulation experts, and HPC experts. On top of this, we can of course mix and match tools. So in a project, you might set out with a very basic UQ approach. For example, you might want to do some quasi Monte Carlo. There's some nice packages, and apply that to your C++ simulation software. Now you may find out that this UQ method is not efficient enough, so you might move to another one and so on, and you can really mix and match components now. So how does this work behind the scenes? Essentially, the idea is that on a theoretical level, a lot of UQ methods assume very few things about the forward model. Those are so-called non-intrusive methods. There are UQ methods that really dig into the problem formulation, and you really have to do hard math and modify existing simulation solvers quite heavily to make them work. These are ones for this which are basically out of scope. But for all of these non-intrusive methods that works, they usually assume that your model is just a function taking a parameter vector onto some kind of an output. That's of course model specific. Some methods may additionally require gradients, form of, well, gradients, Jacobians, Hessians, and so on. But that's about it. This covers really quite a lot of UQ methods, and the same goes, by the way, for optimization. So now Umbridge implements that mathematical interface in software, and specifically by means of a HTTP-based network protocol. Now, to people who don't have much of a background in software, this may be a bit surprising, but it's actually quite established in industry. For example, when you look into microservices, to couple different independent pieces of software to a network like this. And importantly, just like as in microservices, we gain quite a lot of flexibility. Namely, we can use tools from different languages, regardless of technical setup and dependencies and so on, and just link them together regardless of the opposite side of the connection. Likewise, we can go through containerization, and we can go to clusters, and we'll have a closer look at this today. Importantly, of course, you typically don't want to mess around with network protocols when you implement scientific applications. So these little boxes here are supposed to indicate that we provide easy to use integrations for different languages, and in fact also for specific UQ packages, which handle the entire network process behind the scenes. And all that you really have to care about is making a simple function call to one of these mathematical concepts here. So in a real-world project, here's an example of what this might look like. I've shown you this tsunami application before, where we perform Bayesian inversion of the source location of a tsunami given data with a really compute-intensive simulation model. Now that application with traditional tools took us weeks and months to make work because we really had tools that were seriously incompatible. We had to make this work on clusters. And as you know, then of course, just before you want to make this one big run, the cluster shuts down, gets an update, and everything falls apart again. So these are really the experiences you kind of get. You have incompatible ideas about parallelization and so on. By contrast, we tried to do the same application again, this time making use of Umbrage. So this time, the approach was that Anna Reinertz, who take care of the simulation side in this application, set up the simulation code on her laptop. She could use a simple Umbrage test script to ensure that the model returns the outputs that she wanted. Once she was happy with tweaking the model, she could put this in a container. We'll have a look at containers later today, which allowed her to share this simulation model with Mikkel Lykkegaard, who presented yesterday and who was part of this application. Now, he never had to install the simulation code, which, even if you know the code and really know what you're doing on the software side, will take you a day to set up. Likewise, he never had to understand the inner workings of that particular simulation code. It was enough to understand the mathematical concept of how does this simulation source to data prediction map work. We took this up to some simple UQ codes, and specifically because we have an advanced application to his TinyDA code, which handles multi-level delayed acceptance. Now, this code already has an Umbrage integration, so there was nothing specific he had to change about this UQ code in order to operate on this pretty advanced model. Now, once that setup is fine, well, we have an efficient algorithm, but it's still a compute-intensive problem. So I now came in and took Anna's container, again, not installing her model and not understanding the inner workings of it, and put that on a cloud cluster on a Google Kubernetes engine. Now, interestingly, we have an architecture that essentially handles parallelization on clusters. So there was nothing application specific I had to do to make this work. Essentially, I could just grab Anna's container, plug it into that existing framework, and that's it. Now, how could Mikkel then perform UQ on that simulation? Well, I really just had to give him the address of the load balancer on a cluster. Now, to his TinyDA code, there was really no difference compared to running locally. The only difference was results come back much faster and they can run in parallel. And just for good measure, by the way, we throw in a Gaussian process surrogate, which fits in nicely with this architecture and kind of a microservice idea. But in the end, we ran this UQ application inferring the source location of a tsunami under uncertainty using a pretty advanced simulation tool on a couple of thousand cores of a Google Cloud cluster. And it took us, I think, a net 3 days or so ballpark half a week, compared to multiple weeks, and I think it actually dragged out across months with our classical application, where we essentially spent most of our time on technical issues rather than doing actual math. So I hope this gets the idea across that Umbrage really allows us to speed up projects like this, and it handles a lot of the technical issues that you tend to run into just once for all, basically UQ packages and applications. So we can have a look at a quick live demo to show you that this is in fact pretty easy to use. You will later have a look at this in the tutorials in a bit more detail, but let me just give you a brief overview. This is an example of a Python script that uses Umbrage in order to trigger a simulation run. In essence, it's pretty simple. There's some boilerplate that we can ignore. The key part of it is that we set up an Umbrage model and point it to an address where our model is running. Again, the special thing about Umbrage is that now model and UQ are separate applications. So we need to tell Umbrage where that other application is running. We can now ask some details about the model, But the key part is that we can define a parameter vector, pass it into the model. Importantly, that call to the model really just looks like a function call in Python. Behind the scenes, this is going to handle network communication to the server, but to you, it really just looks like any other function call of a function that you might have defined in your own program. Now, as I said, we need a model. So let me spin up a model instance. This is just another Python program implementing a forward model using Umbrage. Now, running that client example, which will trigger an evaluation, I just have to point it to where the model is running. Now, in this case, I'm getting an error. It tells me my input parameter was of length 1, but the model expected length 2. So we'll quickly go back to the client, adapt our input vector to, let's say we just put in the number 100, 1D vector, run the client again, and we get an output. And in fact, we get the second one because this client actually does 2 evaluations in a row. Now, you may guess that this is a pretty simple operation. In fact, this particular model is just multiplying by 2. How do you define a model in Umbrage? Well, this is fairly simple as well. In Python, for example, it comes down to inheriting from an Umbrage model class. And the key part after defining input and output dimensions is really this call function. You receive a parameter vector, you're allowed to do whatever you like with it, and you're supposed to return an output. This particular model is just taking the first input parameter and multiplying it by 2, which is why this client putting in a 100 got back a 200. Now that's not a particularly impressive model, but the interesting thing is, inside this call, you could now trigger whatever kind of simulation run or more advanced computation you would like to have. Optionally, you can also provide gradients, but we'll ignore this for these examples. Let's get back to running this. Now this is a pretty simple application, right? We're just multiplying by 2. And in fact, because both is Python, you could just have written a function multiplying by 2 on your client side. Not particularly impressive. It does get a bit more interesting when we actually run a simulation code now. So let's, for example, quickly have a look at the Umbrage documentation page. In the quick start guide, for example, there's an example for running a model that is containerized. We are now using Docker for containerization. Quick introduction, containers essentially allow you to wrap up software and dependencies in one black box. This one happens to be a published and a public repository. By the way, ignore that it says Podman in my case. I happen to be using a slightly different system, but it's compatible. So now, thanks to containerization, it comes down to that single command to download and run that simulation code on my system. There's no download procedure in this case because I've downloaded that, because I've executed this before and it caches it. But this is really what it comes down to. There's no installation of the simulation software, and this is guaranteed to run on any compatible architecture because the container literally contains all the dependencies and data that it needs to operate on in order for this simulation software to run inside an Umbrage server. Which means that we can now use the exact same client and that we used before in order to talk to this multiplication by 2 and point it to this container. Now again, we expect the model expects a different input that I'm currently passing in. So let's get back to passing in a 2D vector. I'm now running the same client again, just passing in a different vector. And now you can see that this is actually taking a bit longer on the simulation side. Now there's a simulation code triggering inside that container, and the result is coming back. And for another second evaluation, we'll get something similar. So importantly, again, thanks to containerization, there's no installation procedure for the simulation code. And thanks to Umbrage, I can just directly interact with it like with any other Umbrage server and from any Umbrage compatible client. So just to really demonstrate that in practice, the simulation code, by the way, is written in a pretty ugly form of C++ because it's really using code generation and hardware-specific optimizations. So this is kind of tricky to get to run, but thanks to the interface, that was easy. Now, also on the client side, languages don't matter. So we can go to the C++ client, which, just to show you the code, is, well, C++, so it's a bit more verbose, but the essence comes down to the same thing. You can point an Umbrage client to any address wherever your model is running. Localhost, again, would be my own laptop. I can define an input parameter vector, and I can pass that to my model and ask for an evaluation. Again, this looks like just another C++ function call, and it really is, but behind the scenes, it's going to forward the request to our simulation model. Now running that client, you see that the exact same thing happens on the simulation side, except that this time I'm triggering it from C++. In the tutorials, you're also going to see that now, while these are language-specific Umbrage integrations that just give you function calls in the respective language, we also have integrations in UQ tools because some UQ tools have specific ideas about what a model is supposed to look like, and they have their own data types and structures for this. And we fully embed Umbrage in those. So hooking up any of these UQ tools to one of these simulation codes is the exact same procedure. And it doesn't require any adaptation on your end. All right, so I hope this gave you a basic idea of what this will look like. Upcoming topics for today, we'll later have a slightly closer look at containerization, which, as we've just seen in the demo, is really helpful to allowing us to operate on advanced simulation codes and gives us separation of concerns between UQ and simulation experts. We can also have a quick look at the UQ benchmark library that comes with Umbrage, where with I think 25 scientists in total, we've collected interesting simulation problems and formulated UQ problems on them. All of these are available as Docker containers, so you can run those and just benchmark your own methods, or if you want to develop a new method and just try it out on something interesting, you can just grab one of these containers, hook it up to your UQ code via Umbrage, and you're done. Vice versa, by the way, if you're developing UQ codes, I'd really advertise to using Umbrage to you, because this allows you to make your code accessible to basically anyone who has any simulation code lying around, regardless of any technical compatibility issues. Finally, we'll have a quick look at how to parallelize on clusters, and we'll actually try out parallel UQ codes operating with a parallel cluster. The interesting thing, again, being that we can fully abstract simulation codes and UQ from that procedure, but details will come later on. All right, so summing up, Umbrage gives us a unique and universal interface between UQ and simulation models, and it's heavily inspired by math, so it really works for quite a lot of UQ applications. It's by design very easy to use, supports various languages, various UQ tools and frameworks, and it really gives you a lot of opportunities. For example, you can easily share models between collaborators or for reproducibility, and makes it easy to scale up applications as well.